Good morning, our students, and welcome to our today's discussion. Today, we still continue our discussion on sampling distribution of proportions. Yesterday, we looked at the sampling distribution of the difference between two sample proportions. Today, we are looking at sampling distribution of the sample proportions when sampling is done for with replacement. And then we approach this discussion this way. We first of all consider a population. We first of all consider a population. Consider a population. And then let us say that this population exists a binary characteristics. That is to say that every element in this population either possesses a certain attribute or does not possess a certain attribute. And our interest is to estimate the proportion of the elements of this population that possess a certain attribute. And let us say that that proportion is written as P. That is the population proportion of people or elements that possess certain attributes. For us to be able to estimate this proportion correctly, it means, or for us to calculate this proportion correctly, it means that we are going to access all the elements in that population. And you know that it is practically impossible that in a study, one will be able to exhaust all the elements in population. What is that person going to do in order to enable him continue with his research? The person now resort to taking water sample. And then from the sample the person is taking, the person will now be able to estimate what is called the sample proportion. And the person is going to use that sample proportion now to make inference about the population proportion. So meaning that we are going to talk about what sample. We talk about samples. Talk about samples. Okay? And then in these samples now, let us say that the first sample you took or you take is sample 1. And then this sample 1 you are taking, or I put it this way, you talk about what samples, each of size what n. Let us say that the first sample you are going to take contains these elements or items 1, 2, 3, 4, down to what? To size what? N. Then when you come to this sample which you have taken, you begin to consider all the items in the sample one after the other, examining them if they possess the characteristics of what? Of interest. Because your intention is to estimate the proportion of the items in the sample that contains a certain characteristics or attributes. Let us say that when you come here, you check that first element, whether it contains the attribute of interest or whether it does not contain, you check the second one. Let us say that you exhaust checking all of them and then you find out that there are X number of elements in the sample that contains the certain attribute of interest. So you are going to estimate this proportion by saying that P cap is given as X all over what? N. X means the number of items in the sample that contains attribute of interest all over total number of items in that sample. Now, you also come and you take another sample from this population. Let us call it what? Sample 2. And this sample 2 is equally going to contain all the elements from 1 to n. You have 1, you have 2, you have 3, you have 4, down to what? To n. And remember that these elements in sample 1 cannot be exactly the same thing with the elements in what in a sample 2, because it is a random selection, and this time around the sampling is done for with replacement, implying that when you now sample one item into the sample, or you take one observation from the population into the sample, you must return that element in the population before you draw the second one, and you continue in that order till you exhaust the number of items that are supposed to be in your sample. And because this is a random sampling, all the elements cannot be uniform. They cannot be the same in all the samples. So you might equally come and you begin to examine all the elements one by one after the other, looking for the items in the sample that exhibit the characteristics or attribute of what of interest. Let us say that when you are done looking at all of them, that there is X number of what? Of people or items that exhibit a certain characteristics. It is going to be of interest to you that the value of X is going to differ from this sample and this sample. They are not going to be the same thing. The number of attributes here, my X might be something like a 3, but you might finish checking this one now, the number of X might be what, something like 7. So they keep to vary from sample to sample because the elements of the sample are drawn randomly from the population. So you are now going to have that here becomes what? You have what? P estimate is given as what? X all over what? N. And let me distinguish this thing by putting what? 1 here and putting what? 2 here. That is now x1 now, talking about the number of items what? In sample 1 that exhibit certain characteristics. X2 now talking about the number of what? Elements in this sample that exhibit certain characteristics. Then you now also consider what? The third sample. You also take another sample from the population. You do the same thing here up to n. And then you do what you have done in sample 1 and sample 2, and you have that your P what estimate is given as what? X what 3 all over what? N. When you continue to do it now, up to the number of samples that you want to consider, you find out that the values of these estimates of proportion from each of these samples now, they keep to change from sample to sample. So they are not constant. And because they are not constant now, we say that they form a random variable. And that random variable, every random variable has a distribution. So our interest this morning is to determine the distribution of these sample proportions that are taken from a population. That is our interest. And look at the approach that we are going to use to determine the distribution. We are going to pay attention. So I now can show the way that we are going to use to determine the distribution of these sample proportions. Now, let us say that we now come to this particular sample 1 or any of the samples that we want. Then the items in all of these samples are given by, 1, 2, 3, 4, down to what? To n. And let us define a random variable. The function of that random variable is to come to the first element in the sample and check whether it possesses the characteristics of interest or attributes of interest. If it possesses the characteristics of interest or the attribute of interest, that random variable will assign 1 to it. And if it doesn't contain the attribute of interest, it will assign 0 to it. It will equally come to the second item in that sample. Check whether it contains attribute of interest. If it contains attribute of interest, it is going to assign 1 to it, but if it does not contain, it will assign 0. It will come to the third item, check it. If it contains attribute of interest, it will assign what? 1. If it doesn't contain, it will assign what? 0. So you seeing 1 here, seeing 1 here, seeing 1 here, and seeing 0 here implies that the first element contains attribute of interest, the second contains, the third contains, the fourth does not contain. And then the random variable will now keep checking all of them till it arrives at what? At end. Let us define that random variable this way. That we have a random variable what? X, what? I. And this xi is defined as this. Here is 1 and here is what? 0. This one means it contains attribute of interest, which we are going to call success. We call it what? Success. This one means it doesn't contain the attribute of interest, which we are going to call what? Failure. And then we ask ourselves, when this random variable is done, assigning values to each of the items in this sample, depending on if it possesses the characteristics of interest or it doesn't possess the characteristics of interest. We might say, let us now calculate the total number of what? Of items in the sample that contains a characteristic of what? Of interest. What we are going to do is we are going to define a variable called what? Y. What this variable is going to do for me is to count all the elements that possesses the characteristics of what? Of interest. And let us say that if this one possesses the characteristics of interest, it is going to be given 1. If this one possesses, it will be given 1. If this one does not possess, it will be given 0. If this one possesses, it will be given 1. If this one does not possess, it will be given 0 down the what? The line. So this possesses characteristics, possesses characteristics, possesses characteristics. This one doesn't and this one doesn't down the line. If I want to check the total number of elements in this sample that possesses or that possess the characteristics of interest is going to be 1 plus 1 plus 0 plus 1, since adding this 0 here does not change anything here. Like what we have shown here, only 3 possesses characteristics of interest. 1, 2, 3. So you saying 1, 2, plus 0 will still be 2, plus 1 will now be 3, plus 0 will still be what? 3. So it is as good as summing this random variable that assigns either 1 or 0 in each of these samples elements, depending on if they possess the characteristics of interest or not. So this y is going to be given as, the y is going to be given as sum that I is running from what? 1 to what? To n of x what? I. That is how that y is going to be defined. And then if this y is defined this way, it means that y stands for the number of elements that possess the characteristics of interest. In that case, our sample proportion P now, our sample proportion what? P estimate is going to be given as a sum that I is running from 1 to n of xi all over n. And remember that this your sum, I runs from 1 to n of xi, is defined as what? As y. So it implies that my p here, my p cap, is given as y all over what? N. Remember that our interest is to determine the distribution of this proportion. We are going to determine the distribution of this proportion by first of all determining the distribution of what? Of this y. And what is this y? This y is the sum of this random variable. And this random variable has two possible values, 0, 1 or 0, success or failure. And any random variable that contains only 2 possible outcomes is said to be a Bernoulli random variable. And because we are sampling for with replacement, each of these xi is an independent Bernoulli random variable. And we are told that when we sum independent random, Bernoulli random variable, that we are going to get another distribution called binomial distribution. And remember that this y here is the sum of this independent Bernoulli random variable. Because what it means is that this random variable here has two possible outcomes. It can either be 1 for success or it can be 0 for failure. This random variable here has two possible outcomes. It can either be success or failure, 0, 1 and what, and 0. So because this random variable here has two possible outcomes, it means it is an independent Bernoulli random variable. It equally has two possible outcomes here, independent Bernoulli random variable down till up to n number of items. And then this y is the sum of these independent Bernoulli random variables xi. And the sum of independent Bernoulli random variable follows a binomial distribution. So by implication, this our y here, this our y follows a binomial distribution with the parameters what n comma what p, where n means the sample size and p means the population proportion. And we have been taught, or it is known, that the mean of a binomial distribution is given as, the mean of a binomial distribution is given as, the mean of binomial distribution is given as E of what? Of X, I'm using Y, so E of Y is given as what? N what? P. Sorry for my light has gone off. And then the variance var of what y is given as what npq. So I am going to use this knowledge now to be able to find the distribution of this p. So permit me to clean here. So I will now come here. I want to find out the distribution of this p. That is sample estimate of the population proportion. And I'm going to find this thing in terms of what? Of the mean and then the variance. So I will now come here, the mean will be given as, the mean E of P what? Cap will now be given as E, what is my P cap? Y all over N. So it will be given as what? Y all over what? N, which will be given as, when we use this E to open this bracket, it becomes E of what? Y all over what? N. This will be given as E of y is earlier given here as np. So I will now write what? N what? P all over what? N. This n will cancel this n and I'm left with what? P. Which means that the expected value or the mean of the sample proportion is the same thing as the population proportion. It is the same thing as the population what? Proportion. When you talk about the variance, you talk about what? That V of what? P what? Cap is given as, we have what? var. What is my P cap? Y all over N. So I have Y all over what? N. Close the bracket. When I use this variance to open the bracket, I will have what? var of what? Y all over what? N what squared. Because whenever constant comes out of what? The variance sign, that constant ought to be squared. So this becomes, we are earlier told that the variance of y is given as npq. So I have my what? My npq all over what? N what squared. I have n here and I have this square here. So this will cancel this. And what I have becomes what? P what? Q all over what? N. And know you very much well that this PQ can be written as P into 1 minus P all over what? N. Why? Because this Q alone, the Q alone is given as 1 minus what? P. Okay? So this becomes the variance of the sample proportion. The variance of what? Of the sample proportion. It is now going to be given as this. Okay? Now, what again are we talking here? We equally talk about what we call the standard error of the sample proportion. The standard error of the sample proportion. The standard error of the sample proportion is given as standard error of the sample proportion. Sample proportion. It is given as the square root of variance. Square root of variance of what? Of P cap. And we have established that the variance of P cap is given as this. So this thing becomes then variance of P into 1 minus P all over what? N. So that is how to determine the sample proportion or the distribution of sample proportions when we have different samples that are taken. That is sampling distribution of sample proportions. The sampling distribution of a sample proportions. This is how to determine the distribution. We can then conclusively say, that this RP cap follows a distribution with parameter what? P, and then P into 1 minus P all over what? N. We close the what? The bracket. So the sample proportion will follow a distribution with mean the same thing as population proportion and then variance P into 1 minus P all over N. So let us solve one small question from this thing which you have said. So you permit me now to clean here and then we solve one or two questions. The question we want to solve says, a machine produces items and 20% of them are defective. Machine produces item, 20% of it defective. Okay? They say if a sample of n equals to 100, sample of n equals what? 100, is taken with replacement, that we should find I, mean, variance, and the standard error of sample proportions. Mean, variance, and standard error of sample proportion. That is, we should find mean E of what? Of P cap. And then we should equally find our var of P cap. And then we should find STD of what? Of P cap. And remember that this var of P or this expected value of P can be written as, we can write it as what? Mu of P cap. This one can be written as sigma squared of P cap. While this one can be written as a sigma of P what cap. So when we talk about mean, of this random variable p cap, it can be written as expected value or mu of p cap. Vi of p cap can be written as a sigma squared of p cap, and then the standard error of p cap can be written as a sigma p cap. We already have established earlier, first of all, the interest here is on the defective item, and 20% of it is known to be defective. So for us now to find the proportion of defective here, it is going to be that my P, it is going to be that my P is given as what? 20 all over 100, which now becomes what? Here becomes 2 all over what? 10. This knot will go and this knot will go. We have now 2 all over 10. Now, for us now to get the mean, we now say that for our I, our E of P what cap, which is the same thing as mu of P cap. We have shown it earlier that that is equals to what? P. And we have established here that our P is 2 over 10. So this thing becomes what? 2 all over what? 10. For us to get the variance is given as, that is I now. The variance is given as var of what? P what cap is given as sigma squared of P what cap, which is given as, we have it to be P into 1 minus what? P all over what? N. Okay? And then, when we come here, we know quite alright that our P is 2 over 10. So this thing will now be 2 all over 10 into 1 minus 2 all over 10, close the bracket, all over. Our N here is 100, so it becomes what? 100. Once you evaluate this, it becomes what we are looking for. Then when we talk about what the STD, which is I, our STD now, standard error of what? Of our P cap will now be given as square root of variance, square root of sigma squared of what? Of P cap, which will now be square root of this 2 over 10 into 1 minus 2 all over 10 all over 100. So with this, once you evaluate this, you must have arrived at the answer which is needed there. So when you are asked to find a sampling distribution of sample proportion, then this is how you go about it. You first of all show that when different samples are taken from a population and then the sampling is done for with replacement, and from each of the sample that we estimate the proportion of the characteristics of attribute of interest, that the values will keep to change from sample to sample. And our interest is to determine the distribution of that random variable formed by the variations in that sampling the proportion. In fact, some people say that the sampling distribution is the probability distribution that describes the changes in the sample proportion from sample to sample, or when samples are taken repeatedly from a population. And then the moment we show that, we now go about by using a random variable that can assign a value to each of the elements in the sample, which was what we defined earlier to be xi, that assigns either 1 or 0 depending on if it possesses characteristics of interest or not. Then we now come and talk about the sum of that random variable xi, which we use y to represent. And we established that each of the xi is an independent Bernoulli distribution. And the sum of independent Bernoulli distribution is a binomial distribution. And that was what we helped us to conclude, that y follows a binomial distribution with parameters n, p. It is from the distribution of this y that we could determine the distribution of our sample the proportion, sample proportion, P cap. Because our P cap is given as y all over what? N. And then we can then use the distribution of what? Of y to infer or determine the distribution of our P cap. So, and then using that, of course, we arrived that our E of this, that our E of P what cap is given as what? P, and then our var of P cap is given as, we have P into 1 minus P all over N, and then we have that STD is given as square root of P into 1 minus what? P all over what? N. This is exactly what we have succeeded showing this morning. So thank you for your audience, and then stay connected as we keep to unfold our classes on sampling distribution of sample proportions.